Learning objectives. In this chapter, the user will learn the following in detail. Introduction, methods of controlling animation, basic rules of animation, problems peculiar to animation, raster animations, computer animation languages, keyframe systems, motion specifications. Basic rules of animation. Traditional character animation was developed from an art form into an industry at Walt Disney Studio between 1925 and the late 1930s. At the beginning, animation entailed little more than drawing sequence of cartoon panels, a collection of static images that, taken together, made an animated image. As the techniques of animation developed, certain basic principles evolved that became the fundamental rules for character animation and are still in use today. Despite their origins in cartoon character animation, many of them apply equally to realistic 3D animations. These rules are not absolute. Just as much of modern art has moved away from the traditional rules for drawing, many modern animators have moved away from the traditional rules of animation, often with excellent results. Rule 1. Squash and stretch, which is used to indicate the physical properties of an object by distortions of shape. A rubber ball or ball of putty both distort in different ways when dropped on the floor. A bouncing rubber ball might be shown as elongating as it approaches the floor, a precursor to motion blur, flattening out when it hits and then elongating again as it rises. By contrast, a metal sphere hitting the floor might distort very little but might wobble after the impact, exhibiting very small high-frequency distortions. Rule 2 is to use slow in and slow out to help smooth interpolations. Sudden, jerky motions are extremely distracting. This is particularly evident in interpolating the camera position, the point of view from which the animation is drawn or computed. An audience viewing an animation identifies with the camera view, so sudden changes in camera position may make the audience feel motion sickness. Thus, camera changes should be as smooth as possible. Rule 3. That carries over naturally from 2D character animation world to 3D animations, whether they are for the entertainment industry or for scientific visualization, is to stage the action properly. This includes choosing a view that conveys the most information about the events taking place in the animation, and, when possible, isolating events so that only one thing at a time occupies the viewer's attention. In the case of animations for scientific visualization, this isolation may not be possible. The events being simulated may be simultaneous, but it may be possible to view the scene from a position in which the different events occupy different portions of the image, and each can be watched individually without visual clutter from the others. There are many other aspects of the design of animations that are critical. Many of these are matters of eye rather than strict rules, although rules of thumb are gradually evolving. The appropriate use of color is too often ignored, and garish animations in which objects are obscured by the colors are the result. The timing of animations is often driven by computing time instead of by final appearance. No time is given to introducing actions, to spacing them adequately, or to terminating them smoothly, and the resulting action seems to fly by. The details of an animation are given too much attention at the cost of the overall feeling, and the result has no aesthetic appeal. When you are planning an animation, consider these difficulties and allot as much time as possible to aesthetic considerations in the production of the animation. Computer animation languages. Design and control of animation sequences are handled with a set of animation routines. A general-purpose language such as C, Lisp, Pascal, or Fortran is often used to program the animation functions, but several specialized animation languages have been developed. Animation functions include a graphics editor, a keyframe generator, an in-between generator, and standard graphics routines. The graphics editor allows us to design and modify object shapes using spline surfaces, constructive solid geometry methods, and other representation schemes. A typical task in an animation specification is scene description. This includes the positioning of objects and light sources, defining the photometric parameters, light source intensities, and surface illumination properties, and setting the camera parameters, position, orientation, and lens characteristics. Another standard function is action specification. This involves the layout of motion paths for the objects and camera, and we need the usual graphics routines, viewing and perspective transformations, geometric transformations to generate object movements as a function of accelerations or kinematic path specifications, visible surface identification, and the surface rendering operations. Keyframe systems are specialized animation languages designed simply to generate the in-betweens from the user-specified keyframes. Usually, each object in the scene is defined as a set of rigid bodies connected at the joints and with a limited number of degrees of freedom. As an example, the single-arm robot in this figure has 6 degrees of freedom, which are called arm sweep, shoulder swivel, elbow extension, pitch, yaw, and roll. We can extend the number of degrees of freedom for this robot arm to 9 by allowing 3-dimensional translations for the base. Refer figure. If we also allow base rotations, the robot arm can have a total of 12 degrees of freedom. The human body, in comparison, has over 200 degrees of freedom. Parameterized systems allow object motion characteristics to be specified as part of the object definitions. The adjustable parameters control such object characteristics as degrees of freedom, motion limitations, and allowable shape changes. Scripting systems allow object specifications and animation sequences to be defined with user input script. From the script, a library of various objects and motions can be constructed. Introduction. Conventional animation. A conventional animation is created in a fairly fixed sequence. The story for the animation is written, or perhaps merely conceived. Then a storyboard is laid out. A storyboard is an animation in outline form, a high-level sequence of sketches showing the structure and the ideas of the animation. Next, the soundtrack, if any, is recorded. A detailed layout is produced with a drawing for every scene in the animation, and the soundtrack is read, that is, the instance at which significant sounds occur are recorded in order. The detailed layout and the soundtrack are then correlated. Next, certain keyframes of the animation are drawn. These are the frames in which the entities being animated are at extreme or characteristic positions, from which their intermediate positions can be inferred. The intermediate frames are then filled. This is called in-betweening, and a trial film is made, a pencil test. The pencil test frames are then transferred to cells, sheets of acetate film, either by band copying in ink or by photocopying directly onto the cells. Note: cell is a short for celluloid, is a transparent sheet on which objects are drawn or painted for traditional handwritten animation. In multiplane animation, multiple layers of cells are used, some for background that remains constant except perhaps for a translation, and some for foreground characters that change over time. The cells are colored in or painted and are assembled into the correct sequence. Then they are filmed. The people producing the animation have quite distinct roles. Some design the sequence, others draw keyframes, others are strictly in-betweeners, and others work only on painting the fine cells. Because of the use of keyframes and in-betweening, this type of animation is called keyframe animation. The name is also applied to computer-based systems that mimic this process. The organizational process of an animation is described by a storyboard, by a root sheet which describes each scene and the people responsible for the various aspects of producing the scene, and by the exposure sheet, which is an immensely detailed description of the animation. The exposure sheet has one line of information for each frame of the animation, describing the dialogue, the order of all the figures in the frame, the choice of background, and the camera position within the frame. This level of organization detail is essential in producing a coherent animation. The entire process of producing an animation is supposed to be sequential, but is often, especially when done with computers, iterative. The available sound effects may cause the storyboard to be modified slightly. The eventual look of the animation may require that some sequences be expanded, in turn requiring a new soundtrack segment, and so on. Computer assistance. Many stages of conventional animation seem ideally suited to computer assistance, especially in-betweening and coloring, which can be done using the seed-fill techniques. Before the computer can be used, the drawings must be digitized. This can be done by using optical scanning, by tracing the drawings with a data tablet, or by producing the original drawings with a drawing program in the first place. The drawings may need to be post-processed, that is, filtered, to clean up any glitches arising from the input process, especially optical scanning, and to smooth the contours somewhat. The composition stage, in which the foreground and background figures are combined to generate the individual frames for the final animation, can be done with the image composition technique. By placing several small low-resolution frames of an animation in a rectangular array, the equivalent of a pencil test can be generated using the pan-zoom feature available in some frame buffers. The frame buffer can take a particular portion of such an image, the portion consisting of one low-resolution frame, move it to the center of the screen, panning, and then enlarge it to fill the entire screen, zooming. This process can be repeated on the several frames of the animation stored in the single image. If done fast enough, it gives the effect of continuity. Since each frame of the animation is reduced to a very small part of the total image, typically 1/25th or 1/36th, and is then expanded to fill the screen, this process effectively lowers the display device's resolution. Nonetheless, these low-resolution sequences can be helpful in giving a sense of an animation, thus acting as a kind of pencil test. Interpolation. The problem of in-betweening is amenable to computer-based methods as well, but many problems arise. Although a human in-betweener can perceive the circumstance of the object being interpolated, is it a falling ball or a rolling ball, a computer-based system is typically given only the starting and ending positions. The easiest interpolation in such a situation is linear interpolation. Given the values Vs and Ve of some attribute position, color, size in the starting and ending frames, the value Vt at intermediate frame is Vt equals 1 minus t into Vs plus t into Ve. As the value t ranges from 0 to 1, the value of Vt varies smoothly from Vs to Ve. Linear interpolation, sometimes called lerping, linear interpolation, although adequate in some circumstances, has many limitations. Simple animation effects. A few simple computer animation tricks that can all be done in real time. These were some of the first techniques developed, and they are therefore hardware-oriented. The use of color lookup tables, LUTs, in a frame buffer, and the process of double buffering describe image compositing by color table manipulations. The simplest method is to cycle the colors in the LUT to replace color I with color I-1, mod n, where n is the number of colors in the table, thus changing the colors of the variaces of the image. This figure shows a source, a sink, and a pipe going between them. Each piece of the figure is labeled with its LUT index. The LUT is shown at the right. By cycling colors 1 through 5, we can generate an animation of material flowing through the pipe. Using this LUT animation is a great deal faster than sending an entire new pix map to the frame buffer for each frame. Assuming 8 color bits per pixel in a 640 by 512 frame buffer, a single image contains 320 KB of information. Transferring a new image to the frame buffer every 30th of a second requires a bandwidth of over 9 B per second, which is well beyond the capacity of most small computers. On the other hand, new values for the LUT can be sent very rapidly, since LUTs are typically of the order of a few hundred to a few thousand bytes. LUT animation tends to look jerky, since the colors change suddenly. This effect can be softened somewhat by taking a color to be made visible and changing its LUT entry gradually over several frames from the background color to its new color, and then similarly fading it out as the next LUT entry is being faded in. LUT animation can be combined with the pan-zoom movie technique described previously to make longer pan-zoom movies with less color resolution. To make a very long 2-color pan-zoom movie on a frame buffer with 8 planes of memory. For example, For example, we can generate 200 frames of an animation, each at 1/25th of full screen resolution. Frames 1 through 25 are arranged in a single image to be used for a pan-zoom movie. The same is done with frames 26 through 50 and so on up to frames 176 through 200, giving a total of 8 bitmaps. These are combined on a pixel-by-pixel basis into a single 8-bit deep image, which is then downloaded to the frame buffer. We make all the alert entries black except entry 0000001, which we make white. We then run a 25-frame pan-zoom movie and see the first 25 images of the animation. Then we set entry 0000001 to black and entry 0000010 to white. Running another 25-frame pan-zoom movie shows us the next 25 images. Continuing in this fashion, we see the full 200-frame animation. By allocating several planes to each image, we can generate shorter pan-zoom movies with additional bits of color. The hardware-based animation technique called sprites. A sprite is a small rectangular region of memory that is mixed with the rest of the frame buffer memory at the video level. The location of the sprite at any time is specified in registers in the frame buffer, so altering the values in these registers causes the sprite to move. The sprites may hide the frame buffer values at each pixel or may be blended with them. We can use sprites to implement cursors in frame buffers and also to generate animations by moving the sprite or sprites around on top of a background image. Some frame buffers have been designed to allow several sprites with different priorities, so that some sprites can be on top of others. One of the most popular uses of sprites is in video games, where the animation in the game may consist almost entirely of sprites moving over a fixed background. Since the location and size of each sprite are stored in registers, it is easy to check for collisions between sprites, which further enhances the use of sprites in this application. Solved problems. What are the 4 steps of animation? Storyboard layout, defining the objects of animation, specification in the keyframe, in-betweening of the keyframes. What is a storyboard? It defines the motion sequence as a set of basic events that are take place. What is in-between? In-between is a process of generating intermediate frames between the keyframes. Keyframe systems. We generate each set of in-betweens from the specification of 2 or more keyframes. Motion paths can be given with kinematic description as a set of spline curves, or the motions can be physically based by specifying the forces acting on the objects to be animated. For complex scenes, we can separate the frames into individual components or objects called cells, celluloid transparencies, an acronym from cartoon animation. Given the animation paths, we can interpolate the positions of individual objects between any 2 times. With complex object transformations, the shapes of objects may change over time. Examples are clothes, facial features, magnified detail, evolving shapes, exploding or disintegrating objects, and transforming one object into another object. If all surfaces are described with polygon meshes, then the number of edges per polygon can change from one frame to the next. Thus, the total number of line segments can be different in different frames. Morphing. Transformation of object shapes from one form to another is called morphing, which is the shortened form of metamorphosis. Morphing methods can be applied to any motion or transition involving a change in shape. Given 2 keyframes for an object transformation, we first adjust the object specification in one of the frames so that the number of polygon edges or the number of vertices is the same for the 2 frames. This pre-processing step is illustrated in this figure. A straight line segment in keyframe K is transformed into 2 line segments in keyframes K plus 1. Since keyframe K plus 1 has an extra vertex, we add a vertex between vertices 1 and 2 in keyframe K to balance the number of vertices and edges in the 2 keyframes. Using linear interpolation to generate the in-betweens, we transition the added vertex in keyframe K into vertex 3' along the straight line path shown in this figure. An example of a triangle linearly expanding into a quadrilateral is given in this figure. The following figures show examples of morphing in television advertising. We can state general preprocessing rules for equalizing keyframes in terms of either the number of edges or the number of vertices to be added to a keyframe. Suppose we equalize the edge count, and parameters LK and LK plus 1 denote the number of line segments in 2 consecutive frames. We then define Lmax equals max of LK, LK plus 1, Lmin, min of LK and LK plus 1, and NE and NS as follows. Then the pre-processing is accomplished by 1. Dividing NE edges of keyframe min into NS plus 1 sections. 2. Dividing the remaining lines of keyframe min into NS sections. As an example, if LK is 15 and LK plus 1 is 11, we would divide 4 lines of keyframe K plus 1 into 2 sections each. The remaining lines of keyframe K plus 1 are left intact. If we equalize the vertex count, we can use parameters Vk and Vk plus 1 to denote the number of vertices in the 2 consecutive frames. In this case, we define Vmax equals max of Vk, Vk plus 1, and Vmin equals min of Vk and Vk plus 1, and NIS and NP are given by the equations shown on the screen. Pre-processing unit vertex count is performed by adding NP points to NIS line sections of keyframe min, adding NP minus 1 points to the remaining edges of keyframe min. For the triangle to quadrilateral example, Vk is 3 and Vk plus 1 is 4. Both NIS and NP are 1. So we would add 1 point to one edge of keyframe. No points would be added to the remaining lines of keyframe K plus 1. Simulating accelerations. Curve fitting techniques are often used to specify the animation paths between keyframes. Given the vertex positions at the keyframes, we can fit the positions with linear or non-linear paths. This figure illustrates a non-linear fit of keyframe positions. This determines the trajectories for the in-betweens. To simulate accelerations, we can adjust the time spacing for the in-betweens. For constant speed, 0 acceleration, we use equal interval time spacing for the in-betweens. Suppose we want n in-betweens for keyframes at times t1 and t2, refer figure. The time interval between keyframes is then divided into n plus 1 subintervals, yielding an in-between spacing of delta t equals t2 minus t1 over n plus 1. We can calculate the time for any in-between as t bj equals t1 plus j delta t, j equals 1, 2, and so on up to n, and determine the values for coordinate positions, color, and other physical parameters. Non-zero accelerations are used to produce realistic displays of speed changes, particularly at the beginning and end of a motion sequence. We can model the startup and slow down portions of an animation path with spline or trigonometric functions. Parabolic and cubic time functions have been applied to acceleration modeling, but trigonometric functions are more commonly used in animation packages. To model increasing speed, positive acceleration, we want the time spacing between frames to increase so that greater changes in position occur as the object moves faster. We can obtain an increasing interval size with the function 1 minus cos theta, where theta lies between 0 and pi by 2. For n in-betweens, the time for the jth in-between would then be calculated as t bj equals t1 plus delta t into 1 minus cos j pi over 2 n plus 1, where j equals 1, 2, and so on up to n, where delta t is the time difference between two keyframes. This figure gives a plot of the trigonometric acceleration function and the in-between spacing for n equals 5. We can model decreasing speed, deceleration, with sin theta in the range theta lying between 0 and pi by 2. The time position for an in-between is now defined as Tbj equals T1 plus delta T of sine j pi over 2 n plus 1 dash, where j equals 1, 2 and so on up to n. A plot of this function and the decreasing size of the time intervals is shown in this figure for 5 in-betweens. Often, motions contain both speedups and slowdowns. We can model a combination of decreasing speed by first increasing the in-between time spacing, then we decrease this spacing. A function to accomplish these time changes is 1 by 2 of 1 minus cos theta, where theta lies between 0 and pi by 2. The time for the jth in-between is now calculated as Tbj equals T1 plus delta T of 1 minus cos j pi over n plus 1 over 2, where j equals 1, 2 and so on up to n, with delta t denoting the time difference for the two keyframes. Time intervals for the moving object first increase, then the time intervals decrease, as shown in this figure. Processing the in-betweens is simplified by initially modeling skeleton wireframe objects. This allows interactive adjustment of motion sequences. After the animation sequence is completely defined, objects can be fully rendered. Methods of controlling animation. Controlling an animation is somewhat independent of the language used for describing it. Most control mechanisms can be adapted for use with various types of languages. Animation control mechanisms range from full explicit control, in which the animator explicitly describes the position and attributes of every object in a scene by means of translations, rotations, and other position and attribute changing operators, to the highly automated control provided by knowledge-based systems and generate the explicit controls that effect the changes necessary to produce the animation. Full explicit control. Explicit control is the simplest sort of animation control. Here the animator provides a description of everything that occurs in the animation, either by specifying simple changes such as scaling, translation, and rotation, or by providing keyframe information and interpolation methods to use between keyframes. This interpolation may be given explicitly or in an interactive system by direct manipulation with a mouse, joystick, data glove, or other input device. The BBOP system provides this interactive sort of control. The underlying object model consists of hierarchical jointed polyhedral objects, that is, stick figures with pivot points between adjacent sticks, and the animator can control the transformation matrices at each of the joints using a joystick or other interactive device. Such interactions specify the transformations at keyframes, and interactive programs define the interpolations between keyframes. Notice that in such a system, a sequence of actions defined between keyframes may be difficult to modify. Extending one action may require shortening the neighboring actions to preserve coherence of the animation. For example, consider an animation in which one ball rolls up and hits another, causing the second ball to roll away. If the first ball is made to move more slowly, the start of the second action, the second ball rolling away, must be delayed. Procedural control. Procedural control is a significant aspect of several other control mechanisms. In particular, physically based systems, the position of one object may influence the motion of another. For example, balls cannot pass through walls. In actor-based systems, the individual actors may pass their positions through other actors in order to affect the other actors' behaviors. Constraint-based systems. Some objects in the physical world move in straight lines, but a great many objects move in a manner determined by the other objects with which they are in contact, and this compound motion may not be linear at all. For example, a ball rolls down an inclined plane. If gravity were the only force acting on the ball would fall straight down. But the plane is also pushing up and sideways, and so the ball rolls down the plane rather than passing through it. We can model such motion by constraints. The ball is constrained to lie on one side of the plane. If it is dropped from a height, it strikes the plane and bounces off, always remaining on the same side. In a similar way, a pendulum swings from a pivot which is a point constraint. Specifying an animated sequence using constraints is often much easier to do than is by specifying using direct control. When physical forces define the constraints, we move into the realm of physically based modeling, especially when the dynamics of the objects are incorporated into the model. Simple constraint-based modeling can generate interesting results. If constraints on a linkage are used to define its possible positions, as in this figure, we can view an animation of the linkage by changing it in a simple way. In the figure, for example, the animator can generate an animation of the linkage just by rotating the drive wheel, as shown in these figures. Sutherland's Sketchpad system was the first to use constraint-based animation of this sort. It allowed the user to generate parts of an assembly in the same way as 2D drawing programs do today. The parts, that is, lines, circles, etc., of an assembly could be constrained by point constraints. This line is free to move, but one end is held fixed at this point. Linkage constraints. These lines must always remain joined end to end, or angular constraints. These lines must always be parallel, or these lines must meet at 60-degree angle. This allowed the user to draw 4 lines in a quadrilateral, put linkage constraints on the corners, to put a point constraint at one corner, and to put angular constraints on opposite sides to make them parallel. This generated a parallelogram with one corner held fixed. Constraints were satisfied by a relaxation technique in which the assembly was moved so that the constraints came closer to being satisfied. Thus, the user could watch an assembly move so as to satisfy constraints gradually. Of course, it is possible to over-constrain a system by requiring, for example, that a line have a length of 1 unit, but that its ends be joined to 2 points that are 3 units apart. The constraints in Sketchpad are described by giving an error function, a function whose value is 0 when a constraint is satisfied and is positive otherwise. Relaxation attempts to make the sum of these functions 0. When it fails, many constraints may be unsatisfied. Similarly, a system may be under-constrained and have many solutions that satisfy all the constraints. In this case, the relaxation technique finds one solution that is close to the initial configuration. Boning's Similar Thing Lab was really a meta system. It provided a mechanism for defining systems like Sketchpad, but a user could define a system for modeling electrical circuits in the same framework. This system design was later improved to include a graphical interface. A system once designed provided a world in which a user could build experiments. In a world meant to model geometry, for instance, the user could instantiate lines, point constraints, midpoint constraints, and so on, and then could move the assembly under those constraints. This figure shows an example. The user has instantiated 4 midpoint segments with midpoints, has constrained their ends to be joined, and has also drawn 4 lines between adjacent midpoints. The user can vary the outer quadrilateral and observe that the inner quadrilateral always remains a parallelogram. The extension of constraint-based animation systems to constraint systems supporting hierarchy and to constraints modeled by the dynamics of physical bodies and the structural characteristics of materials. Tracking live action. Trajectories of objects in the course of an animation can also be generated by tracking of live action. There are a number of methods for doing tracking. Traditional animation has used rotoscoping. A film is made in which people or animals act out the parts of the characters in the animation. Then animators draw over the film, enhancing the backgrounds and replacing the human actors with their animation equivalents. This technique provides exceptionally realistic motion. Alternatively, key points of an object may be digitized from a series of film frames, and then intermediate points may be interpolated to generate similar motion. Another live action technique is to attach some sort of indicator to key points on a person's body. By tracking the positions of the indicators, one can get locations for corresponding key points in an animated model. For example, small lights are attached at key locations on a person, and the positions of these lights are then recorded from several different directions to give a 3D position for each key point at each time. This technique has been used by Ginsberg and Maxwell to form a graphical marionette. The position of a human actor moving about a room is recorded and processed into a real-time video image of the motion. The actor can view this motion to get feedback or the motion that he or she is creating. If the feedback is given through a head-mounted display that can also display pre-recorded segments of animation, the actor can interact with other graphical entities as well. Another sort of interaction mechanism is a data glove, which measures the position and orientation of the wearer's hand, as well as the flexion and hyperextension of each finger joint. This device can be used to describe motion sequences in an animation as well, much like a 3D data tablet. Just as 2D motion can be described by drawing P-curves, 3D motion, including orientation, can be described by moving the data glove. Actors. The use of actors is a high-level form of procedural control. An actor is an animation in a small program invoked once per frame to determine the characteristics of some object in the animation. An actor, in the course of its one per frame execution, may send messages to other actors to control their behaviors. Thus, we could construct a train by letting the engine actor respond to some predetermined set of rules, move along the track at a fixed speed, while also sending the second car in the train the message, "Place yourself on the track," with your forward end at the back end of the engine. Each car would pass a similar message to the next car, and the cars would all follow the engine. Such actors were originally derived from a similar notion on Smalltalk and other languages, and were the center of the ASAS animation system. The concept has been developed further to include actors with wide range of behaviors that they can execute depending on the circumstances. Kinematics and dynamics. Kinematics refers to the positions and velocities of points. A kinematic description of a scene, for example, might say the cube is at the origin at time 1 equals 0. It moves with a constant acceleration in the direction 1, 1, 5 thereafter. By contrast, dynamics takes into account the physical laws that govern kinematics, Newton's laws of motion for large bodies, the Euler-Lagrange equations for fluids, etc. A particle moves with an acceleration proportional to the forces acting on it, and the proportionality constant is the mass of the particle. Thus, a dynamic description of a scene might be: at time t equals 0 seconds, the cube is at a position 0 meters, 100 meters, 0 meters. The cube has a mass of 100 grams. The force of gravity acts on the cube. Naturally, the result of a dynamic simulation of such model is that the cube falls. Both kinematics and dynamics can be inverted. That is, we can ask the question, what must the constant velocity of the cube be for it to reach position 1242 in 5 seconds, or what force must we apply to the cube to make it get to 1242 in 5 seconds. For simple systems, these sort of questions may have unique answers. For more complicated ones, especially the hierarchical models, there may be large families of solutions. Such approaches to the modeling are called inverse kinematics and inverse dynamics, in contrast to the forward kinematics and dynamics already described. For example, if you want to scratch your ear, you move your hand to your ear, but when it gets there, your elbow can be in any number of different positions, close to your body or stuck out sideways. Thus, the motions of your upper and lower arm and wrist are not completely determined by the instruction, "Move your hand to a ear." Solving inverse kinematic problems can therefore be difficult. In general, it is easier to solve equations with unique solutions than it is to solve ones with multiple solutions. So if we add constraints to the problem, for example, make the potential energy of your arm as small as possible at each stage of the motion, then the solution may become unique. Note that you are constrained by the way that your body is constructed and by other objects in the environment. Scratching your ear is more difficult when you're wearing a spacesuit than it is when you're wearing a bathing suit. This type of problem, especially in the animation of articulated human figures, has received wide attention. The systems of equations arising from such inverse problems are typically solved by numerical iteration techniques. The starting point for the iteration may influence the results profoundly. For example, whether a robot's arms reach under a table or above it to grab an object on the other side depends on whether they are above or below the table on this side, and the iterative techniques may also take a long time to converge. Dynamic models using constraints have also been studied. In this case, the dynamics of the model may be much more complex. For example, the force that a floor exerts on the bottom of your foot is proportional to your weight, assuming for the moment that neither you nor the floor is moving. In general, the force of the floor on your foot, even if you're walking or running, is exactly enough to prevent your foot from moving into the floor. That is to say, the force may not be known a priori from the physics of the situation. To simulate the dynamic behavior of such a system, we can use dynamic constraints, which are forces that are adjusted to act on an object so as either to achieve or to maintain some condition. When the forces necessary to maintain a constraint have been computed, the dynamics of the model can then be derived by standard numerical techniques. By adding forces that act to satisfy a constraint, we can generate animations showing the course of events while the constraint is being satisfied, much as in Sketchpad. For example, constraining the end of a chain to connect to a post makes it move from where it is toward the post. Physically based animation. The dynamics we have described are examples of physically based animations. So in animated form are the physically based models of cloth, plasticity, and rigid body motions. These models are based on simulations of the evolution of physical systems. Various formulations of classical mechanical behavior have been developed. They all represent the evolution of a physical system as a solution to a system of partial differential equations. The solutions to these equations can be found with numerical analysis packages and can be used to derive animation sequences. Motion specifications. There are several ways in which the motions of objects can be specified in an animation system. We can define motions in very explicit terms, or we can use more abstract or more general approaches. Direct motion specification. The most straightforward method for defining a motion sequence is direct specification of the motion parameters. Here we explicitly give the rotation angles and translation vectors. Then the geometric transformation matrices are applied to transform coordinate positions. Alternatively, we could use an approximating equation to specify certain kinds of motions. We can approximate the path of a bouncing ball, for instance, with a damped, rectified sine curve, refer figure, where A is the initial amplitude, omega is the angular frequency, theta 0 is the phase angle, and k is the damping constant. These methods can be used for simple user-programmed animation sequences. Goal-directed systems. At the opposite extreme, we can specify the motions that are to take place in general terms that abstractly describe the actions. These systems are referred to as goal-directed because they determine specific motion parameters given the goals of the animation. For example, we could specify that we want an object to walk or to run to a particular destination. Or we could state that we want an object to pick up some other specified object. The input directives are then interpreted in terms of component motions that will accomplish the selected task. Human motions, for instance, can be defined as a hierarchical structure of submotions for the torso, limbs, and so forth. Kinematics and dynamics. We can also construct animation sequences using kinematic or dynamic descriptions. With a kinematic description, we specify the animation by giving motion parameters, position, velocity, and acceleration, without reference to the forces that cause the motion. For constant velocity, that is zero acceleration, we designate the motions of rigid bodies in a scene by giving an initial position and velocity vector for each object. As an example, if a velocity is specified as 3, 0, and -4 km per second, then this vector gives a direction for the straight line motion path and the speed, magnitude of velocity, is 5 km per second. If you also specify the accelerations, rate of change of velocity, we can generate speedups, slowdowns, and curved motion paths. Kinematic specification of a motion can also be given by simply describing the motion path. This is often used using spline curves. An alternate approach is to use inverse kinematics. Here we specify the initial and final positions of objects at specified times, and the motion parameters are computed by the system. For example, assuming zero accelerations, we can determine the constant velocity that will accomplish the movement of an object from the initial position to the final position. This method is often used with complex objects by giving the positions and orientations of an end node of an object, such as a hand or foot. This system then determines the motion parameters of other nodes to accomplish the desired motion. Dynamic descriptions, on the other hand, require the specification of the forces that produce the velocities and accelerations. Descriptions of object behavior under the influence of forces are generally referred to as a physically based modeling. Examples of forces affecting object motion include electromagnetic, gravitational, friction, and other mechanical forces. Object motions are obtained from the force equations describing physical laws, such as Newton's laws of motion for gravitational and friction processes, Euler or Navier-Stokes equations describing fluid flow, and Maxwell's equations for electromagnetic forces. For example, the general form of Newton's second law for a particle of mass m is F equals d by dt of mv, with F as the force vector and v as the velocity vector. If mass is constant, we solve the equation F equals ma, where a is the acceleration vector. Otherwise, mass is a function of time, as in relativistic or the motions of space vehicles that consume measurable amounts of fuel per unit of time. We can also use inverse dynamics to obtain the forces, given the initial and final positions of objects and the type of motion. Applications of physically based modeling include complex rigid body systems and such non-rigid systems as cloth and plastic materials. Typically, numerical methods are used to obtain the motion parameters incrementally from the dynamical equations using initial conditions or boundary values. Solved problems. What is morphing? Transformation of object shape from one form to another is called morphing. How many frames per second are required for a motion film? Answer: 24. How many keyframes are required for 2-minute film sequence? Solution: 2 into 60 into 24 frames, 2880 frames. Problems peculiar to animation. Just as moving from 2D to 3D graphics introduced many new problems and challenges, the change from 3D to 4D, the addition of the time dimension, poses special problems as well. One of these problems is temporal aliasing. Just as the aliasing problems in 2D and 3D graphics are partially solved by increasing the screen resolution, the temporal aliasing problems in animation can be partially solved by increasing temporal resolution. Of course, another aspect of the 2D solution is anti-aliasing. The corresponding solution in 3D is temporal anti-aliasing. Another problem in 4D rendering is the requirement that we render many very similar images. The images in an ideal animation do not change much from one frame to the next. If they did, we would get jerky changes from frame to frame. This problem is a lot like that of rendering multiple scan lines in a 2D image. Each scan line, on the average, looks a lot like the one above it. Just as scanline renderers take advantage of this inter-scan line coherence, it is possible to take advantage of the inter-frame coherence as well. For ray tracing, we do this by thinking of the entire animation as occupying a box in 4D, space, time, 3 spatial directions, and 1 time direction. Each object as it moves through time describes a region of 4D space-time. For example, a sphere that does not move at all describes a spherical tube in 4D. The corresponding situation in 3D is shown in this figure. If you make the 2D animation of a circle shown in part A, the corresponding box in 3D space-time is that shown in part B. The circle sweeps out a circular cylinder in space-time. For the 4D case, each image rendered corresponds to taking a 2D picture of a 3D slice of the 4D space-time. That is to say, we cast rays from a particular space-time point x, y, z, t, whose direction vectors have a time component of 0, so that all rays hit points whose time coordinate is also t. By applying the usual space subdivision tricks for ray tracing to this 4D space-time, we can save a lot of time. A single hyperspace subdivision can be used for the entire course of the animation, so the time spent in creating the space subdivision does not need to be repeated once per frame. High temporal resolution, many frames per second, may seem unnecessary. After all, video motion seems smooth, and it is achieved at only 30 fps, frames per second. Movies at 24 fps often have a jerkiness about them, especially when large objects are moving fast close to the viewer, as sometimes happens in a panning action. Wagon wheels in movies sometimes appear to roll backward because of strobing. Higher temporal resolution helps to solve these problems. Doubling the number of frames per second lets the wagon wheel turn twice as fast before it seems to turn backward, and it certainly helps to smooth out the motion of fast-moving objects on the screen. The new show scan technology involves making and showing movies at 60 fps on a 70mm film. This produces a bigger picture, which therefore occupies a larger portion of the visual field and produces much smoother motion. Temporal anti-aliasing can be done by taking multiple samples of a signal and computing their weighted average. In this case, the multiple samples must be in the time direction rather than the spatial direction, so we compute the intensity at a point in the image for several sequential times and weight these to get a value at a particular frame. Many approaches to temporal aliasing problems have been developed. Supersampling, box filtering in the time domain, and all the other tricks, including post-filtering from spatial anti-aliasing, have been applied. Another trick for reducing temporal aliasing deserves mention: animation on fields. A conventional video image is traced twice. All the even-numbered scan lines are drawn, then all the odd-numbered ones, and so on. Each scan line is redrawn every 1/30th of a second, but the even-numbered and odd-numbered scan lines are drawn in two different passes. Thus, the electron beam passes over the screen 60 times per second. If the colors of the pixels of the even-numbered scan lines are computed at time t in the animation, and those for the odd-numbered scan lines are computed at time t plus 1/60 second, and these are composed into a single pix map, and this process is iterated for each frame. Then when the animation is displayed, the effect is something like a 60 fps animation, even though each scan line is refreshed only every 1/30th of a second. This trick has some cost. The still frames from an animation do not look as good as they might, since they are composed of images taken at two different times, and they thus seem to flicker if shown on an interlaced display. Also, twice as many frames must be rendered, so twice as many interpolated positions of the objects must be computed, and so on. Despite these drawbacks, the technique is widely employed in the computer animation industry. At the other extreme in animation is the process of animating on 2s or 3s, and so on, in which the animation is produced at a temporal resolution lower than the display's refresh rate. Typically, each frame of the animation is displayed for 2 frames of video on 2s, so the effective refresh rate for video becomes 12 fps rather than 24 fps. This approach necessarily produces jerkier images if no temporal anti-aliasing is done, or blurrier images if it is. Animating on multiple frames and then filling the intermediate ones can be useful in developing an animation. However, since it allows the animator to get a sense of the animation long before the individual frames have all been created. Raster animation. On raster systems, we can generate real-time animation in limited applications using raster operations. A simple method for translation in the XY plane is to transfer a rectangular block of pixel values from one location to another. Two-dimensional rotations in multiple of 90 degrees are also simple to perform, although we can rotate rectangular blocks of pixels through arbitrary angles using anti-aliasing procedures. To rotate a block of pixels, we need to determine the percent of area coverage for those pixels that overlap the rotated block. Sequences of raster operations can be executed to produce real-time animation of either two-dimensional or three-dimensional objects, as long as we restrict the animation to motions in the projection plane. Then no viewing or visible surface algorithms need to be invoked. We can also animate objects along two-dimensional motion paths using the color table transformations. Here we predefine the object at successive positions along the motion path and set the successive blocks of pixel values to color table entries. We set the pixels at the first position of the object to on values, and we set the pixels at the other object positions to the background color. The animation is then accomplished by changing the color table values so that the object is on at successive positions along the animation path, as the preceding position is set to the background intensity. Refer figure. Conclusion. In this chapter, we have covered the following in detail: Introduction, methods of controlling animation, basic rules of animation, problems peculiar to animation, raster animations, computer animation languages, keyframe systems, motion specifications.